discuss the next module, that is crystal plasticity, for the course Introduction to Crystal Plasticity and Crystal Plasticity. So far we have discussed that continuum plasticity models specifically for isotropic and anisotropic cases, and that plastic behavior of a material when we try to analyze using the continuum plasticity, it may not be directly applicable for crystal plasticity. So this subject actually focused on the plastic deformation behavior of a single crystal, looking into the deformation or motion of the dislocations in a single crystal structure. So to discuss this crystal plasticity, broadly we will try to cover the following topics. First is the crystal imperfections, or crystal defects. Second is what are the different slip systems generally also common in engineering materials, and what are the dislocation geometry and energy and dislocation mechanics. So actually crystal plasticity is more oriented to explain this phenomena using the mechanism of dislocation. So basically we will try to understand that what is the dislocations and how it is impactful to analyze the plastic deformation of a single crystal structure. So let us start with the crystal imperfection or crystal defects. So before do that, we'll try to review what we discussed to analyze the crystal structure of different materials. So basic structure, for example, FCC, BCC and SCP structure. So first, what is the crystalline material? Regular repetitive arrangement of the atoms or ions over a long range, which is long range in the sense that it is more than 100 nanometer, then that structure is called crystalline structure. But non-crystalline structure or amorphous material, that is called arrangement of the atoms, actually holds good for a short range. Maybe one example is that glass, which is the non-crystalline structure. So in the sense that whether it is long range or short range, this is a relative matter depending upon the scale of analysis where we are focusing to do this crystal structure or to explain the structure of different materials. So single crystal structure consists of one large crystal. For example, chip made from silicon is the one of the single crystal structure, but it may consist of several unit cells. Polycrystalline material, many small crystals with varying orientation, and actually we have tried to explain the continuum plasticity model, which is the aggregate behavior of the different polycrystalline behavior. Now, to analyze the crystal structure, we actually covered the following topics. First was the theoretical density of the material. If you know what is the specific crystal structure of a material, whether it is BCC, FCC or SCP, we can find out the theoretical density of the material. Then we discussed the packing fraction of the crystal structure, that actually within the unit cell, what is the volume of the unit cell occupied by the atoms, that actually represents the packing fraction of a specific crystal structure. Then we discussed the radius ratio of interstitial sites. So within the atoms, regular arrangement of the atoms, there will be some interstitial sites. So that sites is very much important in the sense that size by the ratio of the interstitial as well as the outer side, which create actually interstitial cells, the radius of that atom is important to know. And we have discussed that for different type of crystal structure, the radius ratio actually varies, and accordingly we can analyze the type of structure of a specific material. Then we discuss the planar density and linear density of the atoms along one plane or maybe along one direction. So the planar density actually represents the number of atoms exist one specified plane. Linear density is the similar way, number of atoms exist one specific direction. These are the all important parameters to analyze in the crystal structure that actually try to characterize for the different mechanical behavior of the materials when you try to focus on the one specific crystal or one specific unit cell of a specific material. Then we discuss different crystallography direction and planes in terms of the Miller indices of a specific crystal structure, and that actually helpful quickly to identify different plane, close packed plane or specific direction or close packed direction. And also we learn about that how we can construct the different planes or directions in a unit cell. Last was the allotropic transformation. So one single material can exist different type of crystal structure depending upon the condition, whether temperature range, and that transformation actually indicates that when there is a change of the crystal structure from one, for example, BCC to FCC or vice versa, then it must be accompanied with the change of the volume, because the arrangement of the atoms actually changes from when the crystal structure changes from one to another. So that allotropic transformation is sometimes helpful to find out what is the change of the volume fraction within the unit cell when there is a change of the allotropic transformation, and how actually it influences the structural form. This actually helpful to understand the plastic deformation behavior when you try to analyze the specifically the change of the volume, and that actually induce some amount of the strain, and this is very much confined to the analyze within the microstructure of a specific material or maybe polycrystalline structure of a specific material. So this actually helpful to understand the crystal structure of materials, and it will be helpful for further discussion or further advancements of the topics. Now here we are trying to represent that four basic crystal structure, that is FCC, simple cubic, BCC and ICP structure. All this structure, there is a, I think it is just to review the different parameters involved in the analysis of the crystal structure. For example, simple cubic structure, that there exists some 8 corner atoms and packing efficiency is 52% or packing factor is only 52%, and coordination number is corresponds to that. If you focus on one atoms within the unit cell, how this atom is continuous contact with the surrounding atom, that actually decides the coordination number of a specific material or specific crystal structure. So simple cubic structure is having coordination number 6 only. If you look into the body centered cubic structure, where there one atom exists on the body along with the corner atoms, so it is having packing efficiency 68% and the coordination number is 8 here. But if you look into the hexagonal close pack structure or cubic close pack structure, or we can say the face centered cubic structure, these two structures having the packing efficiency 74% as well as the coordination number of 12. So this FCC and ACP actually having some kind of close relationship, so that we have tried to explain that 4-axis system is used in case of hexagonal close pack structure and 3-axis system is used for the cubic structure, and that correlation can be possible. That means a representation of the 4-axis system in terms of the 3-axis system was possible in this case. Now if we look into that specific arrangement of the atoms, then we can explain what are the close packed planes and directions that we already investigated in case of simple cubic structure, and BCC structure, FCC structure and ACP structure. All these cases, the close packed, first we look into the close packed planes. Actually there is no well defined close packed plane in case of simple cubic structure, BCC structure, but FCC there is having 1-1-1 plane is having close packed plane, and ACP also having the close packed plane 0001 or 0002. So in case of simple cubic and BCC structure, the close packed direction is 100, and BCC is having 1-1-1 direction. Basically the 1-1 direction is the body diagonal direction, and FCC is equal to 1-1-0 direction. That actually represents the face diagonal direction. So if we look into the different structure and their corresponding close packed planes and close packed direction, we can represent, or we can use this tabulated form to know about the close packed planes and close packed direction of different structure. But if we see that SC and BCC structure, actually there is not having well defined close packed plane as compared to the FCC and SCP structure. But till they can be analyzed, there are several other, we can consider the slip will happens for the in several other different planes. We will try to investigate later on what are the slip and how the slip planes we can consider, and how the deformation may happen in the different planes and different direction in case of simple cubic and BCC structure. Apart from that, we have discussed the interstitial sides. That is important, and we are trying to represent here the range of the radius ratio. Actually the radius ratio here are small r, the size of the interstitial, and capital R, the size of the atom surrounding the interstitial side. So that r by r ratio is a variation for the linear, triangle, tetrahedron and octahedron, cubic. These are the radius range we have already discussed. And if you see right hand side, this actually represents the coordination number. So that coordination number of the interstitial side. So that interstitial side, it is accompanied by the surrounding number of atoms. So in this case, for example, in the cubic side is having coordination number 8, and we can directly say the simple cubic structure at the center point we can fix one cubic side, and that cubic side is surrounded by the 8 cornered atoms. So here the coordination number of this cubic side is 8. Similarly, we can analyze the octahedron, tetrahedron sides that we have already discussed, and these octahedron and tetrahedron sides actually exist in case of FCC and BCC in both type of crystal structure. So this was just a review of the crystal structure. Now we'll start to the crystal plasticity. What do we mean by the crystal plasticity and why it is necessary? One thing is that behavior at the macro level is actually controlled by the features of the microscopic level. So when you try to analyze precisely what is the deformation behavior is explained in the microscopic level, and then that microscopic level behavior actually influence the macroscopic behavior. Most of the cases the macroscopic behavior is represented by averaging the behavior which happens in the microscopic level. So but now we'll try to focus what are the deformation behavior at the microscopic level. So to do that one most important thing is that plastic deformation also happens in the single crystal structure, but here the deformation is little bit different as compared to the microscopic level. So here the plastic deformation, that means most aligned or oriented to the plastic anisotropic condition. So here it is important, or here it is very much significant when you try to analyze the microscopic level of deformation. We need to consider the anisotropic deformation behavior of the material. But this behavior is better explained by the dislocations or motion or movement of the dislocations within the crystals. For example, when you try to analyze the continuum plasticity, in this case we started with the deformation behavior from a single tensile test data or relation between the stress and strain, and accordingly we can decide whether it is deformation within the elastic limit or whether it is plastic limit. But in this case we will try to focus on the how the slip will happen in the single crystal structure, and when there is a start of the deformation, plastic deformation happens within the single crystal. So that will try to get it from this overall crystal plasticity, different theories of the crystal plasticity. So crystal plasticity actually provides the constitutive relations due to the microstructural features. Okay, so anisotropy of single crystal properties actually depends on the crystal structure of a specific material and what are the slip system exist within that material. Secondly, the crystallographic structure, that is basically the crystallite orientation, actually brings the anisotropic behavior, and that is very much related to the crystal plasticity. So that behavior we will try to explain by looking into the basic mechanisms, that means the dislocations and the slip mechanism, motion of the dislocations, and finally the hardening of the hardening behavior of this material, simply by explaining the mechanism of dislocation. So single crystal, the mode of deformation actually related to the slip system within the unit cell. Secondly, we'll focus on that stress needed to activate the mode of deformation, that is related to, or that is defined in terms of the critical resolve shear stress. So basically shear stress actually induces the amount of the shear strain, and that introduces the slip within the crystal structure. And finally, reorientation of the single crystal by rotation, that actually is from the structure. But aggregates of the crystal, basically polycrystal, will try to explain all these things. Averaging the stresses and strains will try to explain the plastic deformation of the material. So now, to start with the crystal plasticity, first step is to analyze the what are the crystal defects. So practically, if we look into the structure of a material, and if we focus on the single crystal, it may be consist of the several defects. For example, the defects can be divided into three components. One is the point defect, then line defect, or in other way line defect can be called as the dislocation, and finally the surface defects. So first we look into the point defect and existence of the point defect within the regular arrangement of the atoms of a single crystal structure. So point defects, it involves one atom or ion or a pair of atoms or ions. So normally, if we look into that silicon crystal, so normal impurities in the silicon crystal exist as oxygen. So that happens actually naturally. So that oxygen, existence of the oxygen within the single crystal structure can be considered as a defect exist, and that defects exist in called the point defects. Now if we look into the silicon crystal, but if we add intentionally the phosphorus or boron to improve the electrical conductivity of this material, that can be called as a defect, but that this type of defect is beneficial or to orient the single crystal with some to bring some specific properties or enhance some properties for a single crystal structure. But basically, how we can categorize the different type of point defects? So that actually point represents in terms of a space of a specific atom or interstitial sites here. So first, one type of defect is that is called vacancy. So if you look into the vacancy, it's a simply the point 1 actually represents the defect like vacancy. So here simply missing of the atoms from the regular arrangement of the atoms. So that type of defects is vacancy. Second is the self interstitial. If we look into the point 2, here that interstitial sites, that means when you try to make the regular arrangement of the atoms, and if interstitial position is occupied by the similar kind of atom, then it will create some defect that is called self interstitial. And in this type of defects, that similar type of atoms will try to occupy that position, and she creates some amount of the strain or stress field surrounding certain area. Now interstitial impurity, for example, point 3. In this case, that the interstitial site is occupied that the another atom, but that is smaller in size. So for example, carbon and hydrogen can take that position in case of when you try to react with the iron. So basically the low carbon steel, for example, that carbon acts as an impurity, so that carbon will try to take always the interstitial position, but size of the atoms in this case is smaller as compared to the parent atoms is the what is the in this case it is the with respect to iron atom. So this type of impurity or self interstitial and interstitial impurity, both type of defects happens in case of normal material. Now if you look into the fourth point, that is the corresponds to the substitutional impurity. Here in this case, the actual atom is actually replaced by the other atom, or it is substituted by the other atom. So this type of defects actually called the substitutional impurity. And if you look into that fifth position, that is also substitutional impurity, but in this case the substitutional impurity size is specifically bigger as compared to the parent atoms here. For example, when the making alloy copper and nickel, copper actually create this kind of impurity in the regular structure of a crystal. Okay. So now the different type of point defects can be observed during the solidification or sintering process, or sometimes heat treatment process. We can observe all these types of point defects. Now, number of vacancies per unit volume, so which is very much related to the point defect. So that vacancy number of vacancy creation is depends on the total number of atoms per unit volume and some energy required to form a vacancy, and as well as the temperature. So if you look into this expression here, NV actually represents the number of vacancies per unit volume, and where N is the total number of atoms per unit volume, and it is depends on the exponential of minus QV by RT. So QV is the energy required to form one vacancy, and R is the gas constant, and T is the temperature. So actually the number of vacancy is very much dependent on this parameter, that is temperature. So using this equation we can roughly estimate the number of vacancies created in one specific material depending upon at one specified temperature. So there is also another point defects, like it is called the Frankel defect, that in that case the point 1 actually it creates the one anion or cation. In this case, that is creation of the vacancy at the same times that similar ion will take the interstitial position, so displacing it and produce the interstitial position. So this type of defect is generally called Frankel defect, and metals and covalently bonded materials having this type of general defect, for example zinc sulfide, AgCl, AgBr, that are the typical compound where we observe the Frankel defect. Similarly, Schottky defect also, here the cations and anions actually missing. So in this case the both cation and anion missed one position, so that type of defect is called Schottky defect. And specifically ionically bonding and sedating materials, these type of defects are observed. Examples are magnesium oxide, zirconium ZrO2, but in this case of course it is always try to maintain the electrical neutrality. But this type of defects actually found in the crystal structure having low packing factor material. Now we shift to the line defects, or we can say the line defects as a dislocation. Dislocation is a linear or one-dimensional defect around with some of the atoms are misaligned. So two basic type of dislocation, edge dislocation and the screw dislocation. That is the representation of the dislocation. But if you look into that right hand side figure, here see the for titanium alloy the dislocations are observed. So dislocation is basically we can say that simply misalignment of the atoms or number of atoms, and that actually disturbs the irregular arrangement of the atoms. So several dislocation, and that dislocation can be generated. Dislocation can move from one point to the another point. So this is a one typical representation of the defects, that is specifically represent the dislocation in term, that is called line defects. So basically we represent the dislocation in terms of the unit of the length. Now dislocation actually responsible for the slip phenomena by which most of the deform plastically. So we can better explain by looking into the basic mechanism of the dislocation, the slip phenomena or plastic deformation behavior of the material. Dislocation are also connected to nearly all other mechanical properties, for example such as strain hardening, yield point, creep, fatting and brittle fracture. All these phenomena can be explained using the concept of the dislocation. So it is necessary to understand the what are the dislocations and how we represent the dislocations here. So typical two basic types of dislocation, that means edge and screw dislocation, will be discussed further the what are the edge and screw dislocation. So this dislocation is a simple schematically representation of edge dislocation, and here if you see the schematic representation of the screw dislocation. So it can be explained like that. For example, there is a regular arrangement of the atoms. Now if you look this here, this extra plane of the atoms actually disturb the regular arrangement of the atoms, but it happens during the metal itself. So when there is a existence of the extra plane of atoms inserted in such a way, that actually create the edge dislocation. So this type of dislocation so is with respect to this point, so edge dislocation, and that normal to this plane represents the dislocation line. But in this case the dislocation is characterized in terms of the Burger's vector, will come later on. So this type of, if the configuration of the atoms is like this, so whether there is an extra plane of atoms from the upper side, or other way we can see there is a missing of the atoms from the bottom plane, then that actually produces the dislocated the actual arrangement of the atoms, and this type of dislocation we can call as a edge dislocation. Now screw dislocation, actually when regular arrangement of the atoms is disturbed by screwing or by the shear with respect to that center point. So that center point, and this is the this point we can find out that shearing with respect to that point, regular arrangement of the atoms, and this is the representation of the screw dislocation. And of course this screw dislocation also characterized by the Burger's vector. Now point is that what is the measure of dislocation, and actually what is the dislocation density. So basically the measure of dislocation is the measure of length actually. So simply we represent the dislocation by a line like that, and what is the length of the dislocation, that is the measure of the one dislocation. Now dislocation density. So dislocation density, probably if we consider the SI unit, so length of the dislocation, for example, it is meter. Now density, what is the total number of dislocation or total length of dislocation within the crystal structure itself. So we simply add on the all the dislocations, and that is representation of the total length divided by the volume. For example, in SI unit it may be meter cube. So finally the dislocation density is basically unit is 1 by meter square, for example. So These are the measurement of the dislocation and dislocation density. We'll further discuss on that topic. Now point is that we characterize the dislocation in terms of the Burgers vector, but how we can represent the Burgers vector and how to find out the Burgers vector. For example, if you look into that left hand side figure, this figure, here we see that figure that is represents the regular arrangement of the atoms, and probably if we start from one point, from this point, and if we make a closed circuit, that representation of the perfect crystal. So closed circuit in the sense that total number of atoms covered on the upper side, it covers the vertical, along the vertical line, what are the numbers, along the horizontal line, these are the numbers are same, and upper side and lower side, it's the same number of atoms it is covering this thing, and it is true for the perfect crystal. We are making this closed circuit. Now if there is introduction of the one extra plane of the atoms, here if you see this extra plane of the atoms actually disturbs the regular arrangement or disturb the perfect crystal structure. So in this case, if we follow the same circuit what we consider for the perfect crystal, and if we start from this point, if we count this number, if we count this number, if we count this number, so it is like that, this count on the line, the total number, count on the slide, total number is same, similarly this side and that side same, and we end at this point. So this gap actually represents the Burgers vector for this specific configuration of the crystal structure. So right and finish to start the convention, so that we follow it, and we can find out the start and finishing point is the total number of, is the balancing, but there is a gap. This gap actually represents the Burgers vector. So that is corresponds to, so this structure actually corresponds to the edge dislocation structure, and this dislocation structure actually, this is the representation of the Burgers vector, but in this case dislocation line, actually if we go back to the previous, so in this case the dislocation actually will represent the Burgers vector like this, but dislocation line is perpendicular to this plane of this screen. So that dislocation Burgers vector actually perpendicular to the edge dislocation line in this case. Similarly for the screw dislocation, actually this represents the Burgers vector, but dislocation line is the along this center. So in this case the screw dislocation, the Burgers vector is actually parallel to the screw dislocation line. Now it will be better understood that how we represent the edge dislocation. So if we see that this is the extra plane of the atom is defined in this figure, and that extra plane of atoms we may be presence or existence from the upper side. So in this case the extra plane of the atoms, and this plane is considered as the, in case of edge dislocation, this plane is considered as the slip plane, because slip will happen along on this plane, and this extra half plane, due to the presence of the extra half plane, this is the representation of the direction of the Burgers vector, but at the same time the normal to that, or on this plane, normal to this plane, that actually represents the direction of the dislocation line vector. So here it is the dislocation line vector and it is the Burgers vector. So in case of specifically for edge dislocation, this dislocation line vector and the Burgers vector will perpendicular with each other. Now what may be the length of the Burgers vector? For example, one specific material, how we can estimate these things? Actually the Burgers vector representation is the repeat distance along the direction. Repeat distance is the shortest distance of the atomic arrangement. So other way B is the shortest lattice translation. For example, in case of simple cubic structure, actually the shortest repeat distance means when you consider the atomic arrangement along one specific direction. So in this case, the distance from one atom to the next atom, and that distance, what is the possible combination of the several possible combination of the direction within the unit cell, or that direction exists several combination of the plane. So on that plane, on the specific direction, what is the shortest distance between the two atoms, that can be considered as a full dislocation, or that can be considered as a measure of the Burgers vector. So in case of simple cubic structure, the shortest distance actually exists along the edge. So that means the direction, maybe we can say 1, 0, 0. But in case of BCC structure or FCC structure, we can see that BCC structure, body centered structure, the shortest distance along the body diagonal. So along the body diagonal, there are the arrangement of the atoms is like this. The corner atom, body atom, and the another next corner atom. So representation of the Burgers vector in this case, it is this distance. So half of the, we can say the half of the body diagonal. So we can represent this direction is BCC 1, 1, 1, 1. But this represents the direction of the body diagonal, and but repeat distance is the half of that. So half of 1, 1, 1 actually represents the Burgers vector in case of BCC structure. Now what happens in case of FCC structure? In case of FCC structure, the shortest distance actually exists between the two atoms along the phase diagonal. So along the phase diagonal also, similar arrangement of the atoms. So it is the one corner atom, it is another corner atom, and there is in between the phase atoms. So similarly for FCC also, the half of phase diagonal 1, 1, 0. That is that 1, 1, 0 actually represents the phase diagonal. So half of that represents the shortest lattice translation distance. So that is the representation of the Burgers vector. So in general, for Burgers vector for FCC and BCC can be represented by A by 2 and UVW. UVW represents the Miller indices of a specific directions. So or maybe specific direction in the sense here is the close track direction. So the magnitude of that Burgers vector can be represented like this: A by 2 U square plus V square plus W square of root. This is the general convention to find out the Burgers vector of a specific crystal structure. So if we know the lattice parameter for a copper, and copper actually follows the FCC structure, so then we can easily find out the length of the Burgers vector in case of copper. Now if it represents the Burgers other way, for example, Burgers vector representation is like the A by 3, 2, 1, 1 in a cubic crystal component. So components can be represented like that in terms of coordinate 2A by 3 minus A by 3 along 1, 0, 0 direction along x-axis, first component. Second component is along 1, 0, 1 y-axis, for example, and third component say 0, 0, 1 direction. So this is the other way, some representation of the Burgers vector. Now a dislocation in a FCC crystal structure corresponding to the phase slip displacement. So in this case, the FCC structure corresponding to the phase slip displacement, in this case the Burgers vector will be represented along the compact direction. So B is the representation of the A by 2, 1, 1, 0. A is the lattice parameter in this case. So 1, 1, 0, actually this direction is a family of direction. So 1, 1, 0 represents the phase diagonal direction. So these are the typical representation of the Burgers vector, and here we have discussed the representation of the this thing dislocation line. So point is that this represents the dislocation line and this represents the Burgers vector. Now I come to that point, dislocation. So how we can define the dislocation? Actually, dislocation is basically a boundary between the slipped and unslipped parts over a slip plane. So it actually distinguishes between the slipped and the unslipped part. That is the representation of the dislocation. The interaction or the meshing of the extra half plane that we have already discussed with reference to a slip plane actually defines an edge dislocation. The dislocation is characterized by the Burgers vector. If the atoms must move from one equilibrium position to another, then it is considered as one lattice position to another for a full dislocation. So if one complete transformation of the one lattice point to the another translation, then that is corresponds to a full dislocation. But it is also possible to partial dislocation, that we'll discuss later on. Now, dislocations actually always tend to have the small Burgers vector as possible. So that is corresponds to the dislocation can be created in such a way that always you will try to follow the short repeat distance. That means that short repeat distance actually exists the common materials. It's in terms of the close pack direction. Now we'll shift to the discussion on the screw dislocation. So in screw dislocation, if we look into that, the first figure actually represents the perfect crystals, and then it is cut and sheared one atom spacing. So it is cut in certain position and there is a shearing action between this on this cutting plane, and if we see the line along which the shearing occurs is a screw dislocation. So with respect to one line, so I see that these are the line. With respect to one line, there is a shifting of the one lattice point that actually represents the screw dislocation. And if we see the Burgers vector is represented that one lattice translation point, so that is corresponding to the B. So this amount is B. It is very much clear from the figure itself. But in this case, the dislocation line actually, or screw dislocation line, is that with respect to the plane, edge of the plane from where the screwing start, or from with respect to the plane with which the shears actually happen. So this line actually representation of the screw dislocation line, which is little bit different from the edge dislocation line. Now the Burgers vector B is required to close a loop of equal atom spacing around the screw dislocation. So similar, if we put it here, the closed circuit, according to the definition of the Burgers vector, then we find out there is a gap of the one atomic spacing, and that gap actually represents the Burgers vector in case of screw dislocation. So both edge and screw dislocation actually represents in terms of the, or characterized in terms of the Burgers vector, and if we count it, when it is corresponds to the full dislocation, then we can say it is correspond to the one lattice point translation in this case. Now practically there may be the possibility of the existence of the mixed dislocation, so existence of both screw as well as the edge dislocation. So a mixed dislocation showing a screw dislocation at the front of the crystal. So showing at the front of the crystal, actually there is a screw dislocation, and the dislocation line is with respect to that direction, and this is the representation of the Burgers vector. But if we look into that, at the same time the direction of the dislocation is parallel to the Burgers, that is true. But in case of edge dislocation, if we see, this is the extra plane of the atoms is actually adding here, and that produces some amount of the dislocation here, edge dislocation, and that is that edge dislocation actually perpendicular to the dislocation, perpendicular to the Burgers vector. So edge dislocation actually exists this internally, and this direction. And screw dislocation exists actually internally this direction. And Barger's vector is direction parallel to the screw dislocation, but S in this case the S dislocation which is perpendicular to the Barger's vector which is perpendicular to the S dislocation in this case. So that mixed dislocation can also be produced, or it is sometimes we observe there is a existence of the mixed dislocation consists of the edge and screw. So these are the some basic idea about the edge dislocation, screw dislocation, and how to represent this dislocation in terms of the Barger's vector. Now we'll shift to the next, the surface defects within the crystal structure. The surface defects, normally if we find out that if there is a difference in the orientation of the atoms, so orientation of the crystals, basically that actually define a boundary between these two. So if you look into that, the orientation of the atoms, orientation of the crystal this direction, and in this the orientation of the atoms is this direction. So then there must be some clear distinguished boundary between these two different orientations. That boundary actually is called as the grain boundary. So one grain is having one orientation, another grain the atoms having another orientation. So this grain boundary, what the typical terms are generally used in the grain boundary, that is small angle grain boundary. So orientation difference may not be very high, so small orientation difference can be considered as a small angle grain boundary. So if orientation difference angle form is very high, then it's a high angle grain boundary can be considered. Now the small angle grain boundary, again having the, we can find out the tilt boundary, we can define the twist boundary, where the tilt boundary actually in terms of the edge dislocation representation, or twist boundary it represents as a correlated in terms of the screw dislocation. So now we need to find out about the tilt angle. Next part I will try to focus on the how to find out the tilt angle. And twin boundaries and stacking faults are the other kind of defects generally we observe. So if we see that tilt boundary, the most simple boundary is the tilt boundary, where the rotation axis is parallel to the boundary of the plane. If you look into this figure, here if you see that the tilt boundary, the rotation axis is parallel to the boundary plane. So if we define this as the color form, that is the boundary plane, and if there is a movement or angle from small angle form is there, that angle actually represents the tilt angle. So that this type of typical boundary is considered as a tilt boundary, where the rotation axis is parallel to the boundary plane. So basically with respect to the rotation axis, so here it is the rotation axis. So rotation axis is actually parallel to the boundary. So this type of boundary is called the tilt boundary. Or twist boundary, where the misorientation occurs around an axis, that axis is perpendicular to the boundary of the plane. So if this is the boundary, but rotation axis is perpendicular to the boundary, and there is a twist between the we can say that between the two grains. So that kind of boundary is called the twist boundary. And twin boundaries, if we look into that, orientation of the grains or orientation of the atoms in such a way that one part and another part, they actually create the mirror image with respect to each other, with respect to certain plane. So that type of plane is basically called the boundary, that is called the twin boundary, and this plane, I think it is defined as the twin plane, and this direction actually basically represents the twin direction. So these are the different type of it is the surface defects that exist within the crystal structure. Now we look into the tilt angle, how we can find out the tilt angle. For example, the angle theta of a tilt boundary is made from 3 dislocation and can be described by the equation below. So this is the 3 dislocation. So represents in the three edge dislocations here, because tilt angle or tilt boundary is corresponds to the edge dislocation. So in this case, that if D is the distance between the two dislocations and B represents the Burgers vectors here. Now if there exist three dislocations, so we can find out the angle theta, but although three dislocation, but it is total corresponds to this actually basically distance is 2D. So that 2D and B is the Burgers vector, and this angular form is the symmetric with respect to only theta by 2. So this relation holds true, that sin theta by 2 equal to B Burgers vector or magnitude of the Burgers vector divided by 2D. So this is the relation of the representation of the tilt angle. Now actually grain boundaries are two-dimensional array of dislocations, and what we have discussed that grain boundary, we can correlate this edge and screw dislocation in this case. So representation of the two-dimensional array of the edge and screw dislocation depending upon the type of the grain boundary, whether it is a tilt boundary or whether it is twist boundary. Now another surface defects, that is called the stacking fault or twin plane. A stacking fault, we understand we have discussed the stacking sequence in case of FCC structure, or we have discussed also the stacking sequence of the HCP crystal structure. The atomic arrangement within the crystal structure exists. If we simply see the HCP structure on the base plane, there is a follow one specific arrangement of the atoms. If we shift to the next plane, there exists on the 3 atoms, and if we next upper plane of the HCP crystal structure, if we look, that is the repetition of the base plane structure. So that sequence of the atoms can be represented like is that on the form of A, for example, next layer if we consider as a different arrangement of the atoms, B, and next layer again repetition of the base plane, so that we can consider another A. So in case of HCP structure, the stacking sequence can be considered like that A, B, like that. But in case of FCC structure, and if we consider the FCC structure stacking sequence or atomic arrangement of the different planes, so that plane is basically normal to the 1-1-1 plane. So 1-1-1 plane, if we consider the 3, if we define in case of FCC structure, if we define the 1-1-1 plane, and if we consider the stacking sequence normal to that plane, it follows like that A, B, C, and similar sequence of the arrangement A, B, C, A, B, C. These are the typical stacking sequence in case of FCC structure, but that stacking sequence actually exists normal to the 1-1-1 plane. Now with the regular arrangement of the stacking sequence, if there is an absence of any layer sequence, then this absence actually creates some amount of the stacking fault. For example, in FCC structure there is a missing of the one layer, so A, C, B, so A, C, B like that, so C actually missing here. So since this missing of the here actually creates that one of the defect, that is called the stacking fault. Actually BA within that layer, this actually follow the sequence of the stacking sequence in case of the HCP structure, because HCP structure only 2 stacking sequence is generally follow and repetition of the same afterwards. Now if we look into that twin plane, so twin plane there is a regular arrangement of the atoms is like that CBA, this is a perfect arrangement, CBA, 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 CBA like that. Now if after deformation, if the sequence of the stacking is like that CAB, CAB, but at the same time other CBA and CBA. So this and this actually with respect to that plane, they actually create the twin plane according to the sequence of the atoms, and this actually happens most of the cases in the plastic deformation, during the plastic deformation. So these are the stacking sequence, grain boundary or stacking fault, twin plane, all is considered as the surface defects. So that means defects actually happens over certain 2D plane or over an area. This type of defects. Now we can find out this. We can see the actual structure of a material. If you see that clearly, the one grain is separated by the grain boundary, and that grain boundary is considered as a defect. So that defect mostly representation in terms of the dislocations. So if you look into this figure also, that schematic representation of the grain boundary, so orientation of the grains are different in this because that orientation is separated by one specific boundary. So these are the representation of the explanation of the different kind of defects exist within the crystal structure itself. Now if we look into that comparison of the different energy associated, definitely when it is associated some amount defect, and that defects actually brings some amount, or it is associated with some amount of the energy within the crystal structure. Now if you compare the different type of defects exist in the crystals and what are the energy associated with the defects, then you will get some idea what is the contribution of the different defects here. So for example, stacking fault in, for example, in aluminium, stacking fault energy per unit area is 200. Example, twin boundary is 120 and grain boundary is 625. So grain boundary energy is more involved here in this case, and most all the other materials also. If you look into that, the energy associated with the different surface defects, then you can find the grain boundary energy is the more amount of energy stored within the material itself. So that means that when material is associated with some defects, and that defects is associated with some amount of the energy. So more defects exist within the material is associated with the more amount of energy is actually deposited, or maybe more amount of energy is actually involved in the crystals. Now we'll come to that point, that to the elementary discussion of the dislocations from the surface defects. Basically we have discussed the surface defects. Now we'll shift to the dislocation and elementary dislocations. Is that we'll try to cover that basic idea about the dislocation source, dislocation motion and slip, critically resolved shear stress and dislocation energy. All these components will be discussed, and probably the next class will next class or next module probably will discuss the dissociation of the dislocations. So first we will try to focus on the dislocation source. Crystals without dislocation is difficult to form. So disturbance in the regular arrangement of the atoms is the simply representation of the dislocation. So there exists some amount of the dislocation in any kind of structure. Dislocation may arise. Dislocation can be increased, or dislocation can be formed from a solidified structure. So in the solidified structure, deviation in the formation of the perfect crystal lattice. So when you solidified structure form, there is automatically form of the at least some amount of the dislocation within the structure itself. Then dislocation can be incorporated through the plastic deformation, and even there is a solid state phase transformation, and the second phase particles that actually introduces some amount of the dislocation within the microstructure. So there are several ways to introduce the different type of crystal structure, and sometimes when you try to form material through the any kind of manufacturing processes, for example either melting, solidification, or through the metal forming processes, so that materials is always subjected to by some amount of the dislocations, or in terms of the motion of the dislocation. So dislocation is always associated with these things, and that dislocation is very much representative of the material, and or maybe very much representative of the crystal defects. What is associated with the always some associated with the some amount of the energy. Now there are several ways to analyze the dislocation. That means how we can dissociate into dislocation with the crystal structure, and how the different dislocation can interact with each other and form the new dislocation. So far we have discussed the S dislocation and the screw dislocation, but the S dislocation can be can be represented like that positive and negative way also, and then similarly screw dislocation can be represented left hand side, left hand screw or right hand screw dislocations, and when they interact with each other, they can sometimes the energy can be balanced depending upon the nature or type of the dislocation interacting, and sometimes the dislocation can be dissociated into small partial dislocation. That we'll discuss later. Now if we try to focus on this specific the dislocation, and here we'll try to explain that what are the specific sources for the basically addition of the dislocation. So one is the Frank rate source. That mechanism actually explain how we can multiply the amount of the dislocation during the plastic deformation. So that one mechanism we call dislocation buoying. If we consider maybe the part of the dislocation, maybe that part of the actual dislocation actually pinned by the solute, presence of the solutes, presence of the interstitial, and presence of the precipitates. Now if we consider one small segment, but that is pinned between the 2 points, so that if we consider this is the one part of the dislocation and pinned by the 2 points, so that 2 points can comes from the solutes or some interstitial or some precipitates. Now if it is subjected to some amount of the shear stress, then it will try to buoying like buoying of a string. So it deformation or can be represented as that buoying of this dislocations of a string. Now we try to mathematically explain this, express the amount of the energy associated with this. For example, if you consider the force is like T here at the pin end, and for example it is making the angle theta, and radial distance is r is defined, and the length of the segmented dislocation is L in this case. It is subjected to amount of the force, that is shear stress, into B is the dislocation, B is the Burgers vector, and L is the length of the dislocation. Now from here with the configuration we can find out that directly that 2t sin theta by 2 is equal to tau VL. So T can be again represented in terms of the energy, dislocation energy. So that we'll discuss later, what is the amount of energy is associated with dislocation, whether it is S dislocation and whether it is screw dislocation. Roughly estimate that amount of the energy, energy per unit dislocation length, and that can be represented by half of G B square. G is the shear modulus of the material, B is the Burgers vector. So from here we can find out that R equal to simply GB by 2 pi. So 2 tau. Tau is the shear stress. Now Frank explained that some dislocations form during the process of the recrystallization, and recrystallization is very much related to any kind of metal forming process, and that happens that this recrystallization actually happens that the recrystallization temperature which is below the melting point temperature of the material. So more dislocations are created during the plastic deformation, and Frank Reed source actually explained a dislocation breeding mechanism. So let us how it works, the Frank Reed source of dislocation, or how this mechanism, how we can explain it. Say for example BC is the segment of the, if you look into this figure, BC is the segment of the dislocation of length n, and it is subjected to a shear stress tau. Now suppose a cross sleeve generates the dislocation segment BC. Now under stress it bows out to form an arc of radius, say for example R. So R can be represented GB by 2 pi, so that segmented radius R. So this radial distance segmented R can be represented like GB by 2 pi. Now stress increases, then R decreases until and unless take 2R equal to B, C equal to L. That means when actually this segmented arc is the semicircular, takes the exactly the semicircular form. So when it takes the semicircular form, then shear stress is equal to basically GB by L. So, or we can say GB by L equal to 2 are exactly that take the semicircular form. So at this point the R becomes unstable with the further straining and forms a closed loop and leaves the original line behind. So after, see, this is the next step. With the further straining, actually it creates the movements of the dislocation. Is the line is like this, and after that it forms the closed loop, and finally it actually forms the closed loop. And that, if you look, there is a closed loop of initial, what was the initial length L, it is created. So again, that means with this mechanism it is explained that similar what we start from the segmented length of the dislocation BC, and we are getting the segmented BC, it is surrounded by this another closed loop. So this is the simply generation of the dislocation. So by using the finite source of dislocation generation mechanism, that we can explain that there is a generation of the dislocation during the deformation of the material. Now next step we try to discuss the dislocation motion. So actually the control of dislocation allow us to manipulate different mechanical properties and understand their temperature dependence. So when the shear force is acting in the direction of the Burgers vector, so this is actually wrong. So these Burgers vectors, actually BURGERS vector is applied to a crystal containing a dislocation. The dislocation can move by breaking bonds between the atoms in one plane. So basically, to break the bonds between the atoms of the plane, we need to apply the amount of the strain so that there is a movement of the dislocation happens. By this process, the dislocation moves through the crystal to produce a step on the exterior of the crystal. So the process by which the dislocation moves and causes a solid deform is called slip. So the process by which the dislocation moves and causes actually it initiates the deformation of a material of a single crystal, that process is called actually slip. We'll try to explain the slip mechanism. Let us look into that, how we can explain these things. So dislocation and plastic deformation. So if you, this is the representation of the atomic arrangement of the atoms, and they exist on the one edge dislocation there. So extra plane of the atoms A at point A, actually the extra plane of the atoms, and that represents that brings the one edge dislocation with this arrangement of the atoms. Now with the application of the amount of the shear stress, if we look into the shear stress, and then there is a gradual movement of the plane of the atoms. If we look into the plane of movement of the plane of the atoms A, B, C, D, clicks, finally it leaves like that A, B, C, D transition, and it will produce the unit step of the slip. So there is a extra plane of the atoms actually brings at the right hand side through application of the shear stress. So this process actually, so we can say that there is a movement of the dislocation from one point to another. That means from movement of the dislocation from on the plane of A, then it moves to plane B, gradually moves to C, gradually moves to D, and finally it brings out. So there is that slip mechanism actually explained through the movement of the dislocation in this case, and that finally it produces the unit step of slip. let us look into the further explanation of these things, dislocation motion. So actually dislocation moves on the slip plane in the slip direction perpendicular to the dislocation line. So let us look into that. And slip direction is the same direction as the Burgers vector. Here if you see, in case of edge dislocation, so there is a slip plane is defined on this, here if you see on the vertical plane here, and direction of the slip as simply movement of the edge dislocation from one point to another point, which direction actually the shear stress is acting. So this representation of the shear, actually this plane represents the shear plane, and from bottom and upper layer there is a movement of the atoms with respect to each other. So this is correspond to the edge dislocation, and if you see, this is the direction of motion is also given, and slip plane is also defined, and dislocation line is also defined. So in this case, if you see, the slip plane is the along the slip plane, the slip direction is actually perpendicular to the dislocation line. So this is the slip direction, and dislocation line in this case is this. So perpendicular with each other in case of edge dislocation. But if you look into the screw dislocation also, here also we follow the similar kind of thing. The shear stress is acting, and direction of the motion, actually shear stress is acting, but direction of the motion is this. And this plane, the horizontal plane actually represents the slip plane, and dislocation, in this case the dislocation line is on the slip plane itself. So by dislocation movement we can represent the slip mechanism, but slip can be represented other way also, to that means here we are trying to represent the slip and the plastic deformation by the dislocation motion, but taking some other example. So dislocation motion is analogous to the caterpillar movement. If you look into these things, the caterpillar actually forms a hump with its position and movement corresponding to this extra half plane in the dislocation model. So let us look into this dislocation model. It is like that only. So this is the arrangement, and there is a one edge dislocation exists, extra plane of the atoms. So it, assuming this is the creation of the hump by the caterpillar. So next stage, then the hump actually shift. So that means that extra plane of the atoms shifting corresponding to the edge dislocation also shift to some other point. Similarly, with further movement, the hump actually of the caterpillar actually shifting to the right hand side according to the shifting of the extra plane of the atoms, or we can say the shifting to the dislocation line in this case. So finally it will take the shape. So it is a complete movement of the dislocation line to the right hand end. So this way, through the movement of the caterpillar by forming a hump, we can explain the motion of the dislocations, and that motion of the dislocation is basically try to represent the complete detach. Actually this, with this movement we can represent the complete separation of the atoms from when it's shifting from one position to the another position. So that slip form is actually represented by the motion of the dislocation. Now slip plane, the plane allowing the easiest slippage. So in the crystal structure, the slip plane is considered as the plane allowing the easiest slippage. So minimize atomic distortion, it corresponds to the minimize atomic distortion energy. So that is associated with the dislocation motion. At the same time, wide interplanar spacing or close pack density or highest planar atomic density, that is corresponds to the close pack plane. So slip will happen mostly in the close pack plane. And slip direction also having the direction of the movement, the highest linear atomic densities on the slip plane, the shortest lattice translation point, basically that is the close pack direction. So we can conclude from the slip behavior of the materials that slip will actually happen is the close pack plane, on that close pack plane in the close pack direction. Now if you look into the slip system in case of FCC structure, that number of independent slip system in the total possible number of combination of the slip planes and direction. So in FCC structure, the slip occurs actually 111 plane, that is the closed pack plane in this case, and on that closed pack plane, that is the 110 direction, that is the closed pack direction. So if we try to represent that slip plane in this case, the FCC structure, so that A, D, F, if we define that plane actually define the slip plane in case of FCC structure, and on that plane, specifically on that plane, the direction 1110. So basically this is a family of directions. So 1110, it represents the several other directions. So that is corresponds to the three different directions, say along the direction B, along the direction C, and along the direction E. So one plane, there is a possible three directions, but in this case, this is the plane, family of the plane actually represents 111 plane, but within the unit cell we can constitute the four different type of 111 plane, four unique different types of plane. So what may be the total possible direction? So one direction is one plane corresponding to three different directions. So then four plane corresponds to total 12 directions. So total 12 slip system in FCC structure is possible. So that means the slip system consists of the 12 possible slip direction in case of FCC structure. Similarly, we can investigate for all other crystal structure different slip system. The slip system actually particular modes of deformation that are activated when stresses are large enough to induce the plastic deformation. So slip will happen on specified plane, one specified directions, but when the applied stress exceeds some amount of the critical stress value, that actually induce the plastic deformation on that plane. Now in that sense, we can define the slip system of the with respect to the slip plane M and slip direction S. So there are many of this slip system for each crystal. So it's like that only. Slip system can be related to the crystal lattice orientation, definitely. So that's why crystal lattice orientation of the symmetric nature of the crystal lattice orientation. If we look into that, so slip can occur in the several orientation. And then with the regular arrangement of the atoms, we can represent that one repetitive representation of the characteristic of the geometric arrangement of the atoms, that is represented by the unit cell here. Now within the unit cell, this is the first figure. If we look into that FCC structure, and we have discussed that FCC structure, the plane is defined the slip plane and corresponding the slip direction. So corresponding total 12 slip system is possible. Similarly, in case of BCC structure, I have already mentioned that BCC structure is not having exactly the very well defined closed packed plane like FCC structure. So possible number of slip system is more in case of BCC structure. So one of that is that M equal to 11, also that slip plane is 110 plane and slip direction is 111. So on that slip plane, there is so it is defined on the slip plane, one of the possible slip plane, and direction is 111. That basically the 111 direction is simply the body diagonal direction. These are the BCC structure, these are the slip system. But in BCC structure, the other slip system also exist. We will discuss later on. In ACP also 12 such slip system exist. Basically that two slip plane is that base plane, and one is the prismatic plane also is defined, and these are the possible slip plane and possible direction also indicated. Now in summary, if we look into that slip system of the different crystal structure, for example FCC structure, this is the plane and this is the corresponding direction, but total number of slip system is 12 here. BCC structure, several plane slip may occur, and on that plane is the direction 111 direction actually slip occurs on that direction. So total possible number of the slip system in case of BCC structure is actually 48, which is more than with respect to the FCC or HCP structure. Similarly, HCP structure, these are the planes, and here we see the slip direction also happens, and we can find out the total 12 number of slip systems exist in case of HCP structure. So in summary, we can say that some slip shifting BCC are only activated at high temperatures, and BCC and FCC have many possible slip systems that we have already possible slip system. So that's why this material is basically the ductile in nature, but in the material is having less possible number of slip system, the nature is generally the brittle. In that cases, the brittle material. So if there is a several possible slip system, the possibility of deformation can be oriented in any direction. But if there is a restricted number of slip system, then possible number of deformation happens within the restricted itself. So then it is the absorbability or maybe of the plastic deformation in this with the restricted number of slip system is less. So that type of material is actually brittle in nature. Now, when you try to explain the slip system exists in the material, and this can be linked with the motion of the dislocation, but at the same time, when the slip will activate it, when it is cross some amount of the strength of the material, so that can be represented in terms of the critical amount of the shear stress is required to initiate the slip system, so that it is possible to plastically deform the material. So to do that, first we look into the theoretical strength of the material. By looking into that, slip occurs by the motion of the dislocation. First, crystal system by slip on the specific crystallographic system that we already discussed, that each plane of the atoms nestles in pockets formed by the plane, and as shear stress is applied to a crystal, the atom above the plane must rise out and slide over until they reach the unstable position. So from this point, they will be spontaneously continue to shear to the right until they reach to a new stable position. So based on these things, we can find out the theoretical strength of a crystals. So look into that. We can consider one specific model, theoretical model, when for example, this is the arrangement of the atoms. Now with the application of the shear stress, there is a position of the atoms changes or slip will happen. So after slip, there is a slipping, the atoms will take the new equilibrium position. So to explain this phenomena, we see that when shear displacement, basically the shear stress is acting this direction, also this, what is the movement of this thing, displacement, x can be represented like that, x can vary, x can be 0, d means complete one atomic space movement, 2d or nd. So that means the lattice restored and so that tau should be 0. So that means when it is reaching with the continuous application of the shear stress, when the atom reaches the next equilibrium positions, then we can assume the shear stress reaches to 0. But tau should be 0 when the displacement can also be half d, 3 by 2d, etc. So this model is better. It seems to most reasonable expression of this equation or phenomena like that, tau equal to tau max into sine 2 pi gamma. So this is the representation of the shear stress, and if we see, there is a one maximum value, tau max, the theoretical shear stress required for slip. Actually, this is the maximum value in this case. And if you look, there is a shear displacement x, and the distance is d, and shear displacement is x here. So shear strength can be represented by x by d. So that shear strength corresponding to the 0, 1, 2 up to n, and gamma is corresponding to the half 3 by 2. It is the nature what way we define the x here, displacement here. So accordingly the shear strength will be like that. Now the model is like that. if you graphically represent this thing, shear stress versus shear strain, it's like that. So it is putting some maximum value. The initial slope actually represents the shear modulus G, the 0 and the negative value. So it is varies in this way with respect to this thing. Now, if the shear stress is less than maximum, the shear strain is elastic and will disappear when the shear stress is released. Now, for the every low value of shear strain, we can find out the tau equal to shear stress equal to G into shear strain. Now, if we do the derivative when very small shear strain value tends to 0, then it is corresponding to G. Now put it this value corresponding to the equation of the relation between the shear stress and shear stress in terms of the shear strain. We can find out this rho tau by dou lambda is twice pi tau x. So in this case, if we see this actually values, or this value actually that represent the slope at shear strain equal to 0. That is the representation of the shear modulus of a material. So that is corresponding to the twice pi tau max equal to G. From here we can find out the maximum shear stress equal to G by 2 pi. But this is a theoretical prediction of the maximum shear stress value. When there is if we consider the application of the shear stress and there is one plane of the atoms is completely displaced, then theoretical prediction tells the maximum shear stress required in this case equal to this term. It's exactly depends on the shear modulus. But real crystal, through the experiments, it is observed the real crystals to some extent the maximum shear stress value actually G by 10 for most of the crystals. So there is a mismatch actually theoretical prediction of this actual practical values or experimental values. Well, what was the reason for that? Actually the theoretical calculation assumed that slip occurs by one entire plane of atoms sliding over another at the same times. But it may not be true always. Crystals have pre-existing defects and with the defined boundaries that already displaced by a unit of slip. The critical stress for slip is the stress required to move a dislocation. So at any instant, slip need only occur at the dislocation rather than over the entire slip plane. So accordingly, we can find out that there is a mismatch of the theoretical prediction with respect to that. Now, if we try to find out the critical values of the shear stress that is required to the movement of the dislocation, and that is called the critical resolved shear stress tau n, and that is the, if you look into that, what is the amount of the critical stress is required, we consider one model like that. Applied stress is this one. So in this case, the applied stress axial load is this one and cross section area is A, and the slip will happening in between some layer, and if we find out that these things, that resolved shear stress we can find out on a specified plane because on that specified plane is the slip plane, and one specified direction, which direction slip will occur, that is the slip direction. So in this case, shear stress can be considered as on the, what is the load is applied on this plane, slip plane divided by area of the cross section, that is the representation of the critical resolved shear stress value. But if we look into that, the resolved shear stress value, that Fs, shear force on that plane is corresponding to the normal force what is applying F cos lambda. That lambda is the angle between the shear force and the normal force in between these two, and this A is area of the cross section of that plane, that is ratio of the A by cos phi. So phi is the angle with respect to the direction of the force, normal force F, and normal to the slip plane direction. Between these two, the angle phi is formed. So if you put these things, so basically we can find out the resolved shear stress acting on the slip plane on the slip direction, that is sigma cos lambda cos phi. That sigma equal to is the normal stress with the applied of the application of the force F. But with this configuration, it's not necessary that phi plus lambda should be always 90 degree. Now, critically resolved shear stress, which is the condition for the dislocation motion. So motion will start once the applied shear stress will cross some critical value. That critical value is called the critically resolved shear stress value. So crystal orientation can make it easy or hard to move the dislocation, so that resolved shear stress, if you look into the resolved shear stress values, and that cos phi cos lambda actually called the Schmidt factor, and this is the position for that. So shear stress equal to 0, or in this case the lambda equal to 0, so it will not move. But when it is considered that phi equal to 45 degree and lambda equal to 45 degree, then resolved shear stress or shear stress equal to sigma by 2. If you look into this orientation, that shear stress equal to 0, phi equal to 90 degree, we can getting the stress value. So the maximum shear stress value will be when phi equal to lambda equal to 45 degree. So that maximum amount of the stress to create the dislocation motion, that amount of the stress is called critical resolved shear stress value. Now if we look into this one example, it will be very clear to that. Consider a single crystal of BCC iron oriented such that a tensile stress is applied along 0, 1, 0 direction. Now we need to compute the resolved shear stress along 1, 1, 1 plane in the 1, 1, 1 direction when the tensile stress of 50 megapascal is applied. Now if slip occurs on a 1, 1, 0 plane and in a 1, 1, 1 direction and critical resolved shear stress equal to 30 megapascal, we need to calculate the magnitude of the applied tensile stress necessary to initiate the yielding. Now we consider the similar configuration, the phi and lambda. For example, if we look into this, phi and lambda we constitute, phi is the normal to the 1, 1, 1, 0 plane because slip occurs on this plane. So phi in between normal to this plane and 0, 1, 0 direction. So 0, 1, 0 direction is actually the applied stress. So phi considered between these two angles, and then lambda between 1, 1, 1, minus 1, 1, 1 direction and 0, 1, 0 direction. So this thus because this is the slip direction. So first one is the slip direction and second one is the direction which direction the force is acting. So we can easily find out. So the Miller index, we put it E1 V1 W1 and E2 V2 W2 accordingly, and we can find out the cos phi between these two directions, and then that is phi equal to 45 degree. The similar way we can find out also lambda is equal to 54.7 degree, and we can find out the resolved shear stress equal to 21.3 megapascal. Now if we try to initiate the yielding, what may be the stress value? So in this case we initiate the yielding. So stress, the normal stress actually required the critical values of the shear stress to initiate the slip with respect to the cos 45 degree and cos 50 phi and lambda what we have calculated before. And here you can find out that 73.4 megapascal is required actually. The maybe you can consider that external load is required to initiate the slip on that specified slip plane and on the specified slip direction. So thank you very much for your kind attention. Now I will start the next class, the remaining part of the dislocations, or in broad we can the remaining part of the crystal plasticity. Thank you.